Testing the equality of two population variances. So we're going to follow the same 4 steps as we've done for the previous hypothesis test. The first step is to state the hypothesis that includes the null and the alternative. Step 2 is to state the level of significance, and this will be given. So for example, if the level of significance is 5%, it would mean that we want to give the null statement a 95% margin of error. The third step is to identify the distribution for the test itself. And since we're testing for the equality of two population variances, the appropriate distribution would be the F distribution, and that's why it's circled. And then step 4 is to actually do the test itself. And I always liken a hypothesis test to a penalty kick. And the way penalty kick works is as follows. So here we have the middle, here we have the goalposts on either side. And if the ball comes anywhere within the net, that's a score. Otherwise, if the ball goes outside of the net, then it's not a goal. What's that got to do with hypothesis testing? In the case of hypothesis testing, the middle here would be the null. So if the sample falls anywhere within the goalpost or the critical values, then we would accept the null. On the other hand, if the samples come in outside of these goalposts, then we would reject the null. So that's why a hypothesis test is exactly identical to penalty kicks. All right, so let's go see how we determine the goalposts. So the goalposts, otherwise referred to as critical values, may be found by specifying 3 parameters. First of all, we need to specify the degrees of freedom for the numerator. So this would be the sample for the numerator sample and -1. And we need the degrees of freedom for the denominator. So we look at the sample size, or the sample size for the second sample, -1. And we also need to specify the tail area. So where's this coming from? Remember, we have 2 populations here. So therefore, we're going to have 2 degrees of freedom. And these degrees of freedom, which is basically sample sizes, are going to come from the 2 samples, which represent the 2 underlying populations. And of course, we have an example coming up. So we'll illustrate how this works. Now, tip. The numerator represents the group that has the higher sample variance. That's the only thing we need to remember. Because again, you've got 2 samples representing 2 populations. So how do you determine which is going to be the numerator sample and which is going to be the denominator? And here's the tip. Always make the group that has the higher variance the numerator. Now, remember the penalty kick analogy? I said first you set up the goalpost and then you see whether the ball came within the goalpost or outside of the goalpost. So the ball, in the context of hypothesis testing, would be the sample itself. And the sample statistic would simply be the ratio of the variances of the 2 samples. And always remembering that the numerator, and this is where the tip comes in from. So the numerator, which is right there, would be the group that has the higher sample variance. So therefore, this ratio of sample variances will always be greater than 1, because the numerator will always be greater than the denominator. And that's exactly the point we make there. So there's your framework, ladies and gentlemen. Now let's put it to use by looking at an example. Here we go. An analyst suspects that small cap volatility is greater than large cap volatility. So therefore, the hypothesis is that the standard deviation of small caps is greater than the standard deviation of large caps. So let's just stop there just for a quick second. And because we really want to know the big picture, this is kind of true, right? Like small cap stocks are more volatile because that's what standard deviation measures. It measures volatility. So yes, if you go back and look at, say, 20 years or 30 years worth of data, small cap stocks are indeed more volatile. But the thing is, we want to use quantitative analysis for definitive proof. So you can't just eyeball historic data and say, yeah, I think small caps are more volatile. You need to do your due diligence, right? And that's where the quant comes in. That's where the hypothesis test comes in. So let's draw a sample and see if it supports this hypothesis. So there it is. We're going to draw a sample. And of course, there's two groups, right? There's the small cap group and the large cap group. So from small caps, we were able to draw 60 months worth of monthly returns. And from large caps, it was 120 observations of monthly returns. Now notice that the number of observations do not have to be the same in both cases. In fact, this is real life. I'll give you an example. With small caps, data may not be readily available. But with large caps, because they're widely traded, data is more available. So that's the first observation we make, is that, you know what, you don't need to have the same sample size from both groups. Now, in any case, so from small caps, we made 60 observations, and the standard deviation of those 60 observations was 2.8%. In other words, how dispersed were these 60 observations around the mean? And we did the same thing with large cap. So from large cap, we drew 120 observations of monthly returns, and the standard deviation of those monthly returns was 2.1%. And again, this represents how dispersed these 120 observations were around the mean. Now remember what we said, between the two groups, we make the one with the higher volatility the numerator. So therefore the small cap is going to be our numerator variable or numerator group. And of course the large cap will be the denominator group. So now we're ready to conduct the hypothesis test. Here we go. Step 1, state the hypothesis. Now, since the hypothesis contains an inequality, we make it the alternative. And I've covered this in a previous module. If you like, you can revisit a previous module and look at my rationale for why we make it the alternative. But in this case, we just want to do the shortcut. And the rule is simple. If you see greater than or equal to in the hypothesis, you make it the alternative. Now, where did you see that? It's right here. It is right there. So I'm going to make this statement my alternative because there's an inequality in there. All right. Now, what else? The other adjustment is that these tests are for variance and not standard deviation. So we need the squares. And then the third modification is that we need to convert the hypothesis into a numeric value. Here's what I mean. This is the original hypothesis, right? But I need to test for a number. See, I don't see a number here. There's no number. So how do I modify that statement so that I get a numeric value? Well, if you find the ratio, so this divided by that, which is what I do here in the next step over here, and with the numerator greater than the denominator, then this ratio should be greater than 1. But now, you see, I have a value that I can test. So do you see how we build in all three modifications into our null and alternative statements? Let me go through it one more time. In the original statement, we had small cap volatility is greater than large cap volatility. So because we saw an inequality, we made it the alternative. Done. That's done. Step 1. Step 2, we need to test for variances, not standard deviation. Done. I did it right there. See that? Great. And what was the third modification? When you're doing a hypothesis test, you need a numerical value so you can test that number. Done. So I reconverted this into a ratio which is greater than 1, and there's the value that we're going to test. So step 3, or modification 3, is done as well. So I just want to show you, ladies and gentlemen, where this came from so that you don't have to memorize. Because if you're going to memorize this, I guarantee you don't have a clue what you're doing, right? And you're going to get the wrong answer, and you're just wasting your time. But the step-by-step shows you how we got there. Now, the alternative and the null are perfect complements. So if the alternative says that this ratio is greater than 1, then the null would say that it's less than or equal to 1. So collectively, they are mutually exhaustive. They represent all possible scenarios. There's no in-betweens. Great. Okay, step 2, level of significance. This will be given to us. So remember what that 5% level of significance means. It means that we want to give the null a 95% acceptance range, because we're using a sample and samples of errors, so we want to give some margin of error around the null. Step 3, identify the distribution for this test, because we're looking at a ratio of variances. It's the F distribution. And then step 4, we do the test. Now, remember we said hypothesis test is like a penalty kick. So the first step is to determine where the goalpost lies for the null range. And in this case, it's a one-tail test. How do we know it's a one-tail test? Because if you look at the null, it's saying accept only values less than 1. So we're just interested on one side of the distribution, not both sides of the distribution. So if that's the case, how do we decide which side of the distribution we want? Well, it says, the null says all values less than 1. So if I picked 0, 0 would be less than 1. So what that tells me is that the null range starts from the leftmost side of the distribution up to some point on the right side of the distribution. In other words, the 95% acceptance range for the null starts from here and ends over there until you've got your 95% range. And by the way, theoretically, what we are plotting on the horizontal axis is the ratio of the two variances. And so the expected value of this distribution is what? Well, what's your default assumption about the two population variances? The default assumption is that they're equal. So if they're equal, numerator and denominator is the same, so the expected value is 1. Now, theoretically, the lowest value possible is if this was 0, right? It's possible for the numerator variance to be 0. So we actually have a finite point on the left side of the distribution. And that's why the distribution for F is not symmetrical, because it has a finite point here. But on the other hand, on the other side, theoretically, you could go to positive infinity, because this variance in the numerator could be positive infinity. Okay, so why am I telling you all this? Well, ladies and gentlemen, if we're going to be plotting the goalpost, we need to see the range for this horizontal axis, right? And here it is. So to get the goalpost, otherwise referred to as F critical, we need to specify the degrees of freedom for the numerator. Now the numerator, if you recall, was the small cap group, because it had the higher variance. So what was the sample size for the small cap groups? It was 60, so 60 minus 1 is 59. And then degrees of freedom for the denominator group, so that would be large cap. We had 120 observations for large cap, minus 1, so that's 119. And then the other thing we need to specify in order to find this goalpost is the tail area. So the tail area would be right there. So that would be 5%. So now what I'm going to do is I'm going to take you to the F table, and we're going to look for these three values and see where the goalpost will lie. So here we are. This is the F table, and we're looking for three things. So first of all, right-hand tail area, which in our case was 5%. So each table is structured based on the tail area you're looking at. So each tail area has its own table. So in this case, we want 0.05. And then the other thing is we need to know the numerator degrees of freedom and denominator degrees of freedom. So our numerator, which is represented by df1, that would be right there. We said we had 59, so the closest number we have is 60. And df2, that's referring to the degrees of freedom for the denominator. And we had 119, but again, you got to go with the closest number, which is 120. So if you triangulate these degrees of freedom, you get a critical value of 1.43. So there's that 1.43. And so where do we put the goalpost? Well, we know that this is 0. We know that the expected value here is 1. So therefore 1.43 must lie somewhere here. So basically what the 1.43 tells us is the following. It says if you want to build a 95% confidence interval for the null, you need to go 1.43 standard units into the distribution. So now the only question is, where does the sample statistic lie? Does it lie somewhere here, in which case we go with the null, or does it lie somewhere here, in which case we go with the alternative? So to get that sample statistic, here it is. We just look at the ratio of the two variances. And of course, you're pulling this data from the sample. So for the small cap sample, the standard deviation was 2.8. But again, ladies and gentlemen, we're testing for variance, not standard deviation. So remember to square it. And the other thing is, you have to square the numerator and the denominator separately. In other words, you can't do 2.8 over 2.1 squared. That would give you a completely different answer. Instead, the proper way is the one that's displayed here. So it's 2.8 squared divided by 2.1 squared for the large cap. And then what you get is you get a sample statistic of 1.78. So let's go have a look at our distribution and see where this 1.78 lies. Again, so look at your key points here. That here is 0. This is 1. The goalpost is at 1.43, so 1.78 must be somewhere there. And then when you look up, you say, oh, that is alternative territory. So therefore, what are you going to do with a null? You're going to reject it. So that's the decision rule. So since the sample stat fell outside the null range, we reject the null, and therefore we accept the alternative. So in English, what does it say? Well, let's see here. When you say accept alternative, why make things up? Didn't we write something down for the alternative? You just said, I accept this, which is the same thing as that, right? So when you say I accept this, you're accepting this. So what you're saying is there is conclusive evidence that the volatility of small caps is larger than the volatility of large caps. And there it is. And you also have to indicate how certain you are about this statement. And here's why, ladies and gentlemen. The fact is, we don't know what the population values are. The whole point of hypothesis testing is that we can't observe the population. So you reach this conclusion from only a sample, which means you're not 100% certain, which means you have to indicate how certain you are in this statement. So how certain are you that small caps are more volatile than large caps? We are 95% certain of this decision because we gave the null a 95% range and we still ended up rejecting it. So therefore, we're 95% confident in this test, but the proper way to express it is that the small cap volatility is larger than the large cap volatility at the 5% level of significance. So there are two different ways of saying how certain you are in your statement, but the general practice is to go with this. But what I always like to do is I like to work backwards and say, instead of saying we're confident at the 5% level of significance, it just makes a lot more sense to say, oh, we're 95% confident in our conclusion.